All right, so thank you, Arnaud, Flora, and Francesca, and everybody that made this series of talk possible, and more generally, thanks to the CY Advanced Studies for hosting me, and the AGM department in Cergy University. It's a pleasure to be here, and my stay was great. And yeah, so the purpose of this today is maybe more to start a conversation, and so I'm hoping that I'll present the general framework where I work, then some of the ideas, some of the tools, and some of the motivations. And then this is really in order to try to give you some ideas of what is of interest. So if you have any questions, just feel free to interrupt. Now, this is about mathematics. And so I know that it can look a little or sound a little obtuse to many people, but please bear with me. I've tried to make it relatable. And so at the beginning, I'll try to get into some maybe vague and abstract notions that might be a little harder to see or to follow. But I promise it's going to get better after the first 10 minutes, and at the very least, there will be more pictures and videos that can be followed. So, all right. Now, okay, let me, go and try to introduce the main thing that I'm trying to understand in my work, and it is dispersion. So now dispersion is something hard to really explain or pin down, and yet it's everywhere. And this is really one of those examples of a universal phenomenon that is under the hood of a lot of things, but it's not so direct. But it's a general way for a system to evolve, whereby this system is going to be made of a lot of different smaller packets, and each of those packets have a life of its own and move in a different way. And so, as a result, this is going to make the system decoherent when everything moves away from each other, and then you can believe that eventually things should start to be simpler, because ultimately everybody is just isolated, and just one person at a time is, or one element at a time is unable to affect a big change. On the other hand, this is done in such a way that the total energy, which is the amount of things that can really affect other things, is conserved. And so in particular, and one way to see this is that the dynamic is reversible, which means that if you observe what happens and you film it, and then after that you watch the movie, if you watch it forward or if you watch it in reverse, those would be two completely possible phenomena, and you would have no way of knowing that one was the one that was filmed and the other one was the one that was filmed in reverse. So this is something that makes it that goes against this fact that things should get better eventually. But at least you can start to see why it should be the case, because if everybody is moving in a different way, then it's possible that initially you have piled all of the energy at one location, and so you have a lot of energy at the same place. But then if all of those packets move away from each other, eventually they will all be isolated. So, okay, that's it for the intuition. Now, one more thing is that it should be different from other general phenomenon that usually often occurs. So for example, dissipation is such a phenomenon. It's how heat behaves, but maybe the most usual way to see it is it's what would govern the way, if you were to pour milk in your coffee, the milk would dissipate in some sense in this case. I mean, the English word is maybe not the best, but this would be how the concentration of milk is in the coffee. And indeed, if you were to take a camera and shoot it, then you would see, just after you've dropped the milk, you would see a small white dot that would gradually become larger and then slowly mix with the brown liquid, and eventually you would just get a clear brown liquid. And now if you were to look at this video in reverse, it would be completely obvious which one was the real video and which one was the video backwards, because you would never expect those two phase to spontaneously separate. So this would be dissipation. You have another phenomenon, which is amplification, which is some kind of inequality enhancement, if you want. It's a phenomenon that where the smaller disturbances tend to get smaller, but then the bigger disturbances tend to be increased and become even bigger. And then there is another phenomenon that is also that you could be at least familiar in a phenomenological sense, which would be friction, which is something that opposes change. So if you're going too fast, it's going to tend to slow you down. If you're going too slowly with respect to everybody else around you, it's going to try to accelerate you. All right, so this was a small discussion of what would be other mechanisms or dynamics. And if it didn't really speak to you, then it doesn't matter because we won't really talk about them later. We'll focus more on dispersion, and I'll try to explain a little bit more about what this is. But first, I would like to say that it's something that, so it's what I try to say, that it's this universal phenomenon in that it really appears or happens in many different settings. It is what governs the sound, for example. And you can see this fact. So, and more generally, it's everything that is associated with a wave. But you can see that if you speak to somebody, then with dispersion, it's going to help carry the sound from your mouth to the ear of whoever you're speaking to. But things will also get gradually better or smaller, and indeed, either in time, because after some time you won't hear anything, or in space, because if you're trying to speak to somebody that is too far away, then the sound will be too attenuated and you won't be able to have a conversation. It's also what describes the propagation of light in certain cases. This is what describes the propagation of the waves in the water or at sea. And this is really what we're going to focus on most. But it also appears in astrophysics and then in plasma physics. So mathematically, at least in the purest case, when you can completely isolate it, it is reasonably well understood. It's understood in terms of a simple partial differential equation, the simplest one and the one that is really the poster child of the dispersive equation is the Schrödinger equation. But more generally, it's some dynamic that involves f, which is the function that contains the information that you're trying to follow. And it does it in a way that is described by three different smaller, So it does it by acting on each of those smaller packets that constitute your f. F is going to be a sum of smaller packets. And if f was one of those individual packets, so you can think of it as the individual brick with which you're going to build your system, or the atoms in your dynamic, if you want. Each of them is going to behave in a relatively simple way. It's going to oscillate at a given velocity, which is given by some function called the dispersion relation. The speed at which it oscillates, so the phase of oscillation are going to move and at a different velocity, but this is given by but in terms of the dispersion relation. But in fact, the real content in your system, the energy, is going to move at yet another velocity, which is a little harder to see, but it's also something that you understand and is completely explicit in mathematical terms. All right, so this is the mathematical description can be understood using those three ideas. Now, if we look at pictures, then hopefully it's going to become a little more clear. So here I have two of those elementary modes of oscillation in black and in blue. And you can see they go up and down. And as they it looks like they're moving to the right. They're moving to the right at a slightly different speed, but except for this, there is really very little that distinguishes one from the other. And indeed, each of those atoms is really just something very simple. What becomes important and where the properties of your system really occur is when you start to superpose them. And so here I've just done simply the sum of those two elementary modes of oscillation, and then you see this red curve. And now you start to see something more interesting. You see that it is naturally isolated in those packets that are, so to enhance them, I've drawn those dashed curves, which the dashed curves should not exist. So it's really the solid curves that is really what is going on, but to emphasize that it's really the sum of those small pockets. So I've drawn it, and you can see, so the dash curve is somehow the units of energy that are apparently slowly moving to the right. They're moving at yet a different speed than whatever you can infer from the blue or the black curve. And inside those packets of energy, my actual solution is still oscillating, and it's oscillating at a different velocity. And if you follow one of the crests, you can see that it is slowly receding from the beginning of the packet all the way to the end of the packet. And so with what I have written before, this would be the phase velocity, whereas the packet moves at the group velocity. And then once you start superposing more and more of those elementary waves, then you start to see more and more complicated phenomena. So here I've really listed 3 of those elementary modes of oscillations. So the black, the blue as before, and then the orange. And in green is the new curve, and you can see because I've added a small additional perturbation, it closely mirrors the red curve that was there before, but it has still a slightly more interesting and complicated behavior. And then in reality, you should really assume that you have a lot of those elementary modes. And if you have, and in general, the general dynamic should move like something more complicated. And here I've drawn 2 random solutions, things that I would try to model in black and in blue, and they correspond to a superposition. So in black, I think it's 25 of those elementary modes, and in blue, it's a little fewer. But the only thing, I mean, don't pay too much attention, just observe that they start to have more complicated behavior that is really just a superposition of those simple things that we saw before, but it's not necessarily so easy to see just with the naked eye. But once you see enough of them, then you can reconstruct the dispersion relation, and then you can really understand everything. So now I need to manage to get to the next one. Okay. All right. So that's it in some sense for dispersion. Now, in general, and I guess this is the case in most for a lot of studies, what you want is not to really just understand one phenomenon in isolation, or you want to isolate it to understand it completely. But where the really interesting phenomenon appears is when you have 2 forces that are really acting on your system and probably trying to fight each other, and the end dynamic comes as a tug of war between those two competing forces. And this is really what happens in nature. And this is also, or in many cases, and this is also what I'm really most focused on. And it's when you have this natural dispersion phenomena that tends to make your system simpler over time, interacts with something else, which would be amplification in this case. So nonlinear interactions. And then the picture becomes a lot more messy, and it's a lot more difficult to really make sense of it, at least in a simple way. But you can at least try, and you can try to continue the same to see to which extent you can apply the same phenomena as before. And so this is what I'm going to try to explain. I was hoping to get a whole hour just talking about dispersion in general, and maybe talk about many different settings where it would happen, but then I realized it would just be too abstract, and if there was no mathematics, so without any mathematics, it would just be some kind of catalog. So instead, I decided to really more focus on one particular application, which really corresponds to something I'm actually working on, and then trying to present it in more depth. And this is the case of the description of the waves in the ocean and how they can be understood. And in this case, it's going to be a competition between dispersion and this nonlinearity that tends to enhance the system. So, all right, so now let's get a bit more specific. And this is more or less the situation that we're trying to understand, at least in some cases. And so the first thing that you can observe is that it's a mess. So ultimately, the punchline, or one of the punchline, is that it's a combination of this dispersion mechanism and the nonlinearity mechanism. And one thing to remember is that this amplification, if you start with something small, it's going to make it even smaller. And so it's not so relevant when you're looking at small waves. And so, but you see, this would be a typical ocean on the right. And all of the disturbances are small, but still you have a lot of different components. And so it's really hard to see what should be the elementary atom, what would be this kind of simple oscillating curves that I have shown you. And then once you start to get into a more agitated system, so something that would really correspond to the sea like that, then it's a lot more messy. And now you really need to understand, well, yeah, so the situation seems to be more complicated and a lot of different things that are going on at the same time. Yet maybe you can start to see that there may be a little bit of structure. You can look at those smaller white crests and see that they seem to be reasonably regularly spaced, but still it is complicated. But then you can try to look at a lot of different cases and hope that at least sometimes you'll be able to spot what would be a simple wave in isolation, the thing that your general system would be a superposition of all of these in a way that is too complicated to comprehend. And so, for example, you can look at a lot of places and times, and this would be one case where you can have some hope. That's a picture taken in the Ile de Ré in France. And then you start really to see that if you squint a little bit, the water is completely flat. And what you really see is a bunch of lines that are regularly aligned perpendicularly. And so maybe this could give you a hint of the structure that is there. And well, the main idea is that what you would like to do is to describe your system as a superposition of now two families of atoms, one that would be given by just the one from the dispersion, which should be the small ripples that you see on the surface. And then another one, which is a new family of objects, that would be those large, big waves, which we will call solitary waves later on. Okay. So let's try to see, how can you start studying this? So what happens here in the water? Well, it turns out that the answer is not necessarily so complicated, at least to pose as a problem. And it's as a set of equations, which are called the water waves equation. They are basically known since the 19th century. So the motion of water was to a large extent already presented by Euler as the first partial differential equation ever written in the 18th century. And then I think Laplace really looked at the case of the waves, which is not just pure water, because you have it's about the interface between water and air. That already asks the question. Cauchy in 1820s, I think, did a lot of really deep work on it. And then in the 19th century, a lot also in the English schools really advanced the theory of waterways. And then in the 20th century, it has really exploded. And so the surprising thing is that what we have seen, all of the pictures that we have seen, which seem to be very different, they can really be described using only three assumptions, but to some extent, they're as close to you can have to first principles. The first one is assuming that the body of water, the fluid, is incompressible, meaning that it can deform. The shape of the water is going to not be the same at all time, but it can only deform by preserving its volume. The total amount of water is really fixed and it doesn't change. It's always going to have to occupy this, the same space, so the same volume. The second assumption is that the particles, so the small particles of water, they have to obey Newton's law, which is really the universal law that describes the mechanics of objects. That says that the force is equal to the acceleration. And since you're trying to describe the evolution of a system, you would like to describe the acceleration. And then in principle, if you were to know this completely, it's everything just follows from that. And so the next question is, what are the forces that would make your system move? And in this case, you have gravity. So this is trying to push the water down. And this is obviously going to try to fight against a wave forming, which is a lump of water that goes up above the general level of the water. You have surface tension, which we will forget from now on, because it's really only relevant if you look at waves that are less than 2 centimeters of length, of wavelength. And so for us, it's not going to matter too much, but it's a force that tries to make the interface, the length of the interface between air and water as small as possible. And then the last one, the last big force is the pressure force. That is a way for the fluid, the water, to make sure that it stays always with the same volume. So if you push somewhere, the liquid has to move somewhere else. And so it's going to push or to pressure the other particle of liquids away. And once you have this, then in principle, that's it. You can just go about and work on and start solving the equations. It would be immensely complicated. Unfortunately, you can do two natural additional assumptions, which are valid in a lot of cases. One is that there is no underlying current. So that would be that your system, that the water is irrotational. And then the other one is that there is no dissipation, this phenomenon that I mentioned at the beginning, and we're just assuming that it's not there. And it's not so relevant, at least if you think of the ocean. But once you have this, then that's it. You know exactly what you have to study. And in principle, if you were to stare long enough at your set of equations, all of the information is encoded there. And you would be able to solve this, one of the main goal of this, which is the next best thing you have as to a prophet, it's being able to solve the Cauchy problem, which is to say, if I have all the information about now, so if I take a picture of the situation at this moment, then I can just solve the equation to predict how the situation is going to be in the future at any given time. And if I can do it, say, with a computer faster than the system can evolve, then I can predict the future. Now, the next question is, what exactly is the information that you really want to follow? Because as we have seen, there is a lot of things happening, but probably many of them are just forced once I know two things of information. And if you think a little bit about it, what you really need to know is what is the surface, what is the interface, how to describe the interface between air and water. And that's it. But you also need to know how it moves over time. So what is the interface between air and water and the velocity of the water, at least at the surface, and then you can recover everything. Okay, so now this is just the equation. This is just to say that this is what they look like. In principle, that contains all of the information. Now we won't really focus more on this. It's if you don't really understand what those symbols mean, don't really bother about it. But it's just to say this is the equation, and this is really the system that we're trying to understand. So what we would really like to describe is what is under the blue curve and the black curve. So above the bottom of the sea and below the air. And so the bottom of the sea doesn't really change. So, and to a first approximation, we can imagine that it's flat because at least in many cases, it's going to be good. Or say you're in a canal. And so what you're really interested in is to understand where is the boundary between air and water. And that's encoded by this. So yeah, that's this blue curve. And the other thing that you would like to know is how is the water moving underneath this curve? So what is this velocity inside? And in principle, you would like to know it everywhere, but because of the way these equations are structured, it really suffices to know it at the boundary, at the upper interface. And in fact, you need this anyway, because this is the thing that is going to tell you how your interface is going to move. Okay. So this is the system that you have to stare at. Now, in principle, once you have the equation, I said, sorry, yeah, good. I said if you stare at them long enough, then you would be able to answer everything. And maybe more precisely, if you feed them into a computer and you were able to work with the computer would be able to tell you how the system is going to evolve. And to a certain extent, then you could say, okay, this is the end of certainly of the modeling and maybe of the mathematics. And indeed, if you were to try to do it with your pen and paper, this would be completely inefficient because you would maybe be able to predict where the system is 1 second later than when you took the picture, but it would take you 2 hours to do that. So you would be better off just watching the movie directly. But mathematics can still come in and answer and look at a few interesting questions that are relevant no matter how powerful your computer is. One of them is this kind of thread that I've tried to start at the beginning and that we're going to follow. And it is, what are the elementary waves? What are really the small atoms in this dynamic that I would like to understand, and that in principle, any general dynamic is just a sum, no matter how complicated, of those atoms. And when do they exist? So as we have seen, even with this simple equation, you do have a few things that are going to be important. For example, the depth of the water is probably going to be important. The fact that here I've looked at a cross section, but in principle, it should really be something in 3 dimensions. Although I guess for simplicity, I'm mostly going to talk about what happens in a cross section, assuming that the wave is long in the other direction, as we have seen in some of the pictures. Okay. The next question that you would like to answer is, how dramatic can the dynamic be? And this is important because we had to make some assumptions when we derived the equation. So for example, the assumption that there was no current, it would be very convenient if we could make sure that if there was no current initially, then there will be no big current that will develop spontaneously by itself. So, and more generally, how well within my assumptions is my system going to stay? And a related question, so if you want, the typical question that people would like to know is, if I have an ocean which is completely at rest, and then I start tapping on the surface slowly, I'm going to produce small ripple. What I would really like to happen is that there will only ever be small ripples. What would be really bad is that I create some small ripples, but at some point they all coalesce into one of those freak waves that can be tens of meters high for without any discernible reason that they appear and then it will disappear. So you see, this is the kind of transfer of energy when I really excite only, make a small excitation, but I let it somehow build up over time, and it can create a very big change. And more generally, I would like to be able to say, okay, can I always understand how my system is going to behave eventually once I stop pushing at it or exerting any other forces? And then another final set of questions that we can ask is, okay, I've presented you the equations, they fit in 3 lines, yet they're really formidably complicated to study. And so they were written down more than 200 years ago, and we have still a very poor understanding of them in general. So would it be able to derive some simpler model? Something that, so one way to give up trying to express everything, but still be able to meaningfully understand some of the information in my system. Maybe I only look at certain type of waves, so I only assume that everything moves in one direction, but then I would like to see, in this case, can I understand it, and do I get some simpler equation? So this is something also important, and maybe we can talk about it later, but at the moment, I would more like to talk about those first 2 points. And maybe more specifically, say a bit more about what are the 2 different families of elementary bricks that you encounter in the evolution of the waves in the ocean. And so one of those families of elementary atoms is linear waves. So solutions of just a linear problem, which is what happens if I tune off this enhancement mechanism, the nonlinearity. So which, if you have something small, its effect is even smaller. So it's not so relevant in any case if you have small waves. And so small waves should be described by those dispersive waves, which I would ask you to believe me, we more or less completely understand in terms of some reasonably simple object. And this is what they look like. And so here I've drawn 2 general solutions. They would correspond to the behavior of 2 small waves in a pond. And so one is in black, the other one is in blue. To visualize them a bit better, so one is as average height 0, and the other one I've put it to have average height 2. But you can see they move. Maybe the blue one would correspond a little better to your idea of what a big wave rolling should be. But both of them should happen. And the only thing that you should really notice at this stage is that they tend to go up and down as much in basically equal way. And then otherwise, they're always moving. But yeah, their feature, so you see, well, yeah, it behaves like that. So okay, this is one of the family of the solutions. And the other family of solutions is what we started to see in this picture at the Ile de Ré. And those are called solitons, or solitary waves. So those have a slightly different story. The first one was spotted by Scott Russell, who was a British engineer in 1834. And then he was following a barge on a canal that suddenly stopped. And then so the barge, as it was moving, was dragging some water with it. And then the barge stopped. And he observed that the wave then overtook the barge and continued on its own. And this is not so surprising. But what was surprising was that it really continued without changing its shape, just moving to the right steadily. And it continued for a really long distance. So you could follow it on horseback 2 to 3 kilometers without really noticing any big effect, except that it gradually became smaller because it interacted with the side of the canal. And so that's interesting because at the time, people thought that because this is a dispersive phenomenon, then you might have some disturbance at some point, let's say when the barge stops, but it should always go reasonably fast to the equilibrium, which would be a calm canal. And they really didn't believe that he had seen a wave that could possibly travel without changing for such a big distance. And so it took more than 50 years for the experts in the physics and mathematics community to really understand that this was indeed something that did exist and that it was in the equation that they had. So somehow they had dismissed it, but without really looking at the model that they already had. And so you can see it on the right. This is, so the people at Watt University decided to do an experiment to recreate this wave that Russell saw. And so this is, I think in early 2000, they recreated it. And so you can see it in the front. And so this is the wave and it's going to continue moving. But once you know that it exists, then you can see that they really happen in many different contexts. And so this is a photo taken at the shore of Hawaii. You see those waves a lot. On the other hand, it's not so easy to see them in complete isolation. And so here you really see something which is as close as you can get to a completely flat sea. And you have only this wave here that is slowly moving towards the shore. Okay. But as I said, those waves, even though they surprised the experts, you could already understand them with the equation that I have presented you. And they're really not so easy to see there, but if you look at a simpler equation, so the Korteweg-De Vries equation, which was exactly, so Korteweg and De Vries derived it from the more complicated water wave equation to understand those objects, then there you can understand it completely in the sense that you have an exact formula that you can write down and you can really see what happens. And what happens is that those solitary waves, they really have a very specific form. They all have the same shape, except for a change of scale. And then you see that, well, one thing that you can see is that this is a new kind of waves. You would not be able to explain it just based on this dispersion alone. It's here because you also have this nonlinearity that tries to take something big and then enhance it and make it even bigger. And so in principle, you would have a disturbance and then it grows, but at some point it saturates because it is counteracted by the dispersion. So it's really some object that is a result of the tug of war of those two mechanisms, dispersion and nonlinearity. And as a result, it keeps some features of both. And so, for example, it has this fact that the bigger you are, the taller you are, the more concentrated. So the wave can be tall and narrow. And in this case, it's going to move quite fast. Or it can be more small and squat. And it's going to be to move more slowly. And then there is a whole, so for every height, you would have one wave that corresponds, that is a solitary wave. You can see that they are different from the waves that I have shown you before as some example of linear waves, because it's purely a wave of elevation. Everywhere the wave is above the water, far away to the right and far away to the left. And something else that you can see once you have the formula, which is not necessary, well, which becomes obvious once you have the formula, but is a qualitative fact that you can also check, is that the speed, so not the speed increases with the height, but it also increases with the depth. And so the speed is given by this formula, at least for the KdV equation. And so it's h would be the height, the height of water under the height of water between the bottom and the average surface. And then a is the amplitude, which is the amplitude of the wave. And so this is really important because it really governs a lot of phenomenon that happens in the ocean. And this is why if you're in very deep ocean, you can have waves that really travel very fast. And this is how you can have tsunamis, for example, that allow a wave on one part of the globe to, say, Chile, for example, to affect Japan in 2 days, which you can think that 2 days is very long. But if you think of the distance involved, it's really tremendous. You need to go really fast to be able to do that. Unfortunately for Japan in this case, because well, if there was some earthquake in Chile before the 20th century, people in Japan would have no way of knowing that something is going to hit them in 2 days because it happened so far away. And as a result, you can also see that when the depth is really big, then they do not exist because they move so fast that before they have a chance to create, they have already moved to infinity. All right. And so now I will try to show a video, which is to tell you why those waves are important to understand. And essentially, it's because this is, well, related to this thing about tsunami, this is one of the best ways that a wave can really move some energy from one place to another. And for us, what is going to be important is that this is what you think that is the most dangerous to the shore and to the beach, is the thing that could the most easily damage the beach. And so I found this video on YouTube, which I thought was really illuminating. So I'm going to share. I need to find it. Let me just a second. And now. And maybe just before, I see that there is a question in the chat. Sorry. I know, sorry. All right, so let me share this video. So this video, I found it on YouTube. And I think what it illustrates is how you can easily create a wave that is going to travel reasonably fast. And even though it's going to be a small wave, ultimately it's going to be able to shoot some water higher than the height of a man. So can you see the video?
Yes.
Okay, very good. So this is, now they have a dam, they are going to open the gate and it's going to create the wave, which is the same as the one that Russell.
Voor mij mag hij.
So it's at the end. That's when it's going to reach here.
Weer niet. Hoezo niet?
Okay. Now back to the presentation. I think this is it. Okay. And so the one thing to really that you could really see from this was, one, it does travel quite fast. The person, even though it was a small wave, the person had to really run to catch up with it, to keep up with it. And second is that if for some reason at the end, for example, you have a beach or a cove that tends to concentrate it at a narrow point, then you can really focus a lot of energy at one point. And does something that is really impressive. In this case, it really shot this lump of water really high. And this is important for this particular problem, which is going to be the final thing I want to talk about. And it's one thing that I'm trying to understand with two collaborators, Emmanuel Dormy and Christophe Lacave. And it's related to what happens to islands, for example, in the Pacific Ocean, where there you have volcanic islands. So it starts with a volcano that the volcano started a long time ago. So erosion has started to erode the side of it. The water has started to erode the side of it. And as a result, you have a lot of islands that would be here on the right and are protected from the ocean by a lagoon. And then after the lagoon, the volcano really drops to the bottom of the floor, and then you have the deep ocean. So this is some system that we're trying to understand. And why is it so important? Well, this picture is not up to scale. So the lagoon is typically 80 centimeters to 1 meter high, deep. Whereas the ocean is more something to the order of 3 to 4 kilometers deep. So really this is basically infinitely deep as opposed to that. The transition, well, it depends on the particular place, but it can be quite steep, although this is exaggerated. So it can be, I think, up to 30 degrees, which counts as steep, but not, well, anyway. And then you have a lagoon, and then you have the island that is here. And one of the questions is, so this picture is reasonably stable. The island has not really changed that much for the last 10,000 years. But now what's going to happen with global warming as the level of the ocean rises, the depth of the lagoon is going to change. And that might really change a lot of the thing that managed to penetrate inside the lagoon and to go and hit the beach. And in particular, what would be really bad is if, because we also are going to have more storms, we're going to have more big waves that come here. And if they all attack the beach and then tend to move the sand from the beach into the deep ocean, which is so deep that then the sand is completely lost, then this would be really bad for the island, on top of the fact that just mechanically with the sea rises, it's going to get smaller. Now in this part, so this is good because it is a problem with reasonably few parameters that you might want to understand. There is one other big player that is not present, is that here you should have a coral reef that probably also has a lot of impact and that you would like to understand also how it is impacted. But okay, one thing at a time. But so this is basically the picture that we would like to understand better. And more precisely, as we have seen, the waves that are really the most damaging, or at least some of the waves that are the most damaging, are the solitons. And the solitons, they can happen in the lagoon because we are in reasonably shallow water. They don't really happen on the ocean unless you're really talking about a tsunami or some other phenomenon that is quite exceptional, that you don't really expect that there would be too many of them, hopefully. But somehow the solitons that are created here, they have to come from somewhere. And so one of the questions is, which is this small elementary brick in the deep ocean that when it comes into this region where the bottom rises steeply is going to create a soliton later. And so to understand that, well, the answer is we really don't have too much of an idea. And there is we don't really have too much good understanding of this picture, but at least we can start to do some experiments numerically and then try to look at some of those simpler models where we could really, in principle, where we could really get more information. And so this is one code that was developed by my collaborators, Emmanuel Dormy and Christophe Lacave, where they really look at this picture. So one of the interesting things is that this is the full equations, the full water wave equation that are being simulated. And this is not something that I want to discuss too much, but believe me, it is really challenging to do it with a computer. even though a computer is really fast and powerful, it requires a lot of ingenuity to be able to simulate these equations because they are really intrinsically very difficult. And the other difficulty is that in this problem, you need to do it on a very large scale to understand what happens. And so then you're really probing the limit. But what is this picture? So in this picture, we want to look at what happens. So ideally, or maybe ideally, but one of the things that would correspond best to the picture would be to have basically infinite depth here, or super deep here, and then shallow here. At the moment, we can do reasonably deep depth here, and then more shallow depth there. And we want to understand what happens when a collision, one of those solitary waves is left by itself. Okay, and I'll just try to show quickly what happens. So you can see that at the beginning, this is really a solitary waves as advertised. It really just moves to the right without any change. And if the bottom were completely flat, it would continue to do that forever. Now the bottom is not completely flat, and at some point it's going to sense what happens with this cliff that is under the water, and it's going to start to sense it, and it's going to create a mess, some collision between the soliton and the obstacle underneath the water. And then after the collision event, you are going to have two things that are going to happen. So something is going to penetrate the lagoon and go on to continue, and then something is going to be reflected. And okay, so this is already quite remarkable that the picture is so simple after the impact. In principle, you would imagine to have a chopped sea here with a lot of complicated behaviors, but as far as the naked eye can see, after say t=40, then you have basically a completely flat surface here and no trace that something really bad happened. The only trace are with those two things that move to the right and to the left. Now the next question is, among what is reflected, how can you understand it, and can you relate it to one of those two small bricks that I told you? One of the bricks being the family of solitons, and then the other brick being the family of linear dispersive waves. And this is not so easy to see, but at least you can start to guess it. And the advantage is that the solitons are so simple in shape that once you have the curve, then you can just try to match it and see if it does. But you can sort of see that here there will be one soliton that is reflected, and then after that, it's only linear dispersion. And you can see it because at the beginning, it's always above the water. But then once it gets into the dispersion, it goes below the water level, and then above, and then below, and then above. And so it continuously oscillates. And this is really one way where you can spot a dispersive wave. Now on the right, well, you can see this same phenomenon that I told you before, that solitons move all the faster that they're on a deep sea. And so now it entered a shallower lagoon, and so it really went a lot more slowly. Yet, this is going to be a superposition of at least two solitons, and one is a lot taller and narrower than the other, and the taller one is going to travel a little faster, and so eventually they should really decouple, and you should really see those two pure atoms of evolution. Unfortunately, here with the code, we can't really follow it too much because the box has to come back down to have no problem with infinity. But what you would like to know is to know what is the future evolution of this if it were able to continue unimpeded for a longer time. And so, well, anyway, you can do this at least by taking scissors and then cutting here and now restarting this data, but now with a very long bottom. And if the bottom doesn't change, then the solution should be a lot easier to simulate. And more generally, you can, once you have a good way to experiment, then you can ask a lot of questions. So for example, with respect to what is the thing that is going to create the solitons, the question would be to start, now I've lost my cursor, to start with a soliton here and then make it move towards the cliff, because this would be like looking at the picture backwards in time, using the fact that the equations are time reversible. If we want to know what can possibly create a soliton, a different way is to start with a soliton and moving backward in time, which, which is possible with these equations. All right, so maybe this is a good place to stop. I hope this was not too confusing. I've tried to give you some overview of, well, the general phenomena that we're trying to study and that are really the players in this tug of war. I've illustrated it with water waves because I think this is the one thing that gives the best picture, and certainly on the web, it is the one topic where you can have more illuminating pictures. The other things, essentially, because they're about more complicated objects, it's just impossible to visualize. And then to try to explain how it corresponds to some really, really physical problem that you would like to be able to solve and to answer this question, for example. But basically, even though people have been studying waterways for 200 years, most of the questions that you could ask, I would answer by, I don't know. And I'm guessing most people would too. But at least we can, we know exactly what is the problem that we have to face, and we can really try to make progress on it. And so this is the game. All right, I'm going to thank you for your attention, and then asking if you have any questions.